Moving on to another test. So this is called the integral test. And so if we're given a sum, remember all of these series we have tests on. So if we're given this sum where this is the nth term, so a sub n can be written as f of n, and we're going to change it to x's. And this function has to be positive, continuous, and decreasing. So positive means above the x-axis, right? Continuous, draw it without lifting your pen, and decreasing, so as we're reading the graph, it's coming down. Okay, so if I find that the integral from 1 to infinity of the function f of x that's made from the f of n, which comes from the nth term, if I find that that function, the integral from 1 to infinity, that converges, then I can say that this series converges also. So remember, when it converges, it goes to a number, right? There's a limit that equals a number. So I do not get what the sum is. I just get to say that this sum converges. If this integral diverges, limit doesn't exist, equals infinity, then I can say that this series is divergent also. Okay, so big deals when we're doing these integrals. That's why I finished off last time. You have to rewrite the integral with a limit and put the t where the infinity was, and you always have to do the integral in x's, right? You have to change it to x's because we can't do integrals in n's. What n's mean are just integers, 1, 2, 3, 4, right? Starts at 1, 2, 3, 4. We can't take the area under a curve that is not continuous. So again, I'm just saying here that the sum does not add up to or have a sum of what this converges to. So when do we want to use this integral test? Because every test has its own time that it's useful. Usually pretty useful if I have an E or an ln in it. So here's one right here. So converge or diverge. Can't use p-test, can't do partial fractions, or, I mean, there's a lot of things I can't do. So let's do this so that I'll do the integral test. So notice it starts at 2. So this is just to make sure that the function's defined, nothing more than that, because if I put in 1, I get ln of 1 is 0 in the denominator. So it starts at 2. So first step is to rewrite it as a limit, putting t where the infinity is. And then I did the u substitution, right? So I kind of did 2 steps at once. So I let u equal ln of x, du is 1 over x dx. So this is u cubed in the denominator. So then I took the antiderivative, u to the negative 2 over negative 2, and I'm going to make sure I remember to put the x's back in. So here's your negative 1/2. I put this in the denominator, u squared, and then I'm going to evaluate it between 2 and t. So plug in the t first for x, subtract off, plugging in the 2. So these two negatives make a positive. Let t go to infinity, so I get 1 over infinity, that's 0. So I get this. So this means that the integral converges. So therefore, I can conclude that this series, or this sum, converges also by the integral test. Let me just say it again. That does not mean that the sum of this is this, right? I just get that the integral converges. I'm sorry, that the sum converges because the integral converges. All right, so I'm going to come back and just kind of do a little bit of a proof of this, why the p-test works. Kind of haven't done that. So you know 1 over n to the p. If p is less than or equal to 1, it diverges. And if p is bigger than 1, it converges, right? So does it mean to converge again? It means that the sum adds up, even if I can't find out what the sum is. And the diverge means it doesn't add up. There's an infinite sum. So let's go over let's draw this 1 over x. So let me remind you, in improper integrals, what you saw was 1 over x squared, that integral converged. So this integral, this improper integral converge has a limit, whereas this one diverges. So they're really close to each other, as are these p-tests. Doesn't make much sense at all that they look so close to each other, then one adds up and one does not. So let's look at this, 1 over x. 1 over x looks like this, right? And I'm kind of going over the comparison test again because it keeps coming up. The comparison test is really important. So this is good for you to have an exercise in looking at it again. Okay, so let's draw some rectangles. So I'm going to start at 1, and I'm going to make rectangles of width 1 to keep it nice and kind of going along with the sum from 1 to infinity. So I'm going to use left-hand endpoints. So my area of my first rectangle would have height f of 1 and width of 1, right? Height f of 1, width of 1. So that's rectangle number 1 right there. So rectangle number 2 will have height f of 2 and width of 1. So that's rectangle number 2. And then height f of 3, right? So you can see the pattern. So these are the areas of the first 4 rectangles that I'm showing here. Okay, so what this is, if I use the function 1 over x, put 1 into the function, put 2 into the function, put 3 into the function, look at that. What is this giving me? This is giving me 1 plus 1/2 plus 1/3 plus 1/4. That is this, isn't it? So this is the sum of 1 over n. Okay, so now here comes the important part. So what do we know about the integral of 1 over x? What do we know about the integral of 1 over x dx? You did it on your homework, and you saw and you know that this diverges. So let me just get a little color going here. So what you know is the area of the red, which is this, adds up to infinity. So what can we conclude about the area of the blue that is more than it? Well, since the area of the blue will be more than the area of the red, that must diverge also. So since this one diverges, this one must diverge also. So that's the proof of the p-test for for p equaling 1. All right, and so the same thing goes. So if I said the same thing, since this diverges, I know this diverges also. And so I could go through and do more of them, but as long as this n, this exponent, is smaller than or equal to 1, this diverges. So that's the p-test. Okay, so let's just go through and practice the p-test because we're going to use it a lot in the next sections. I want to make sure you're really good at it. So I would take the time to rewrite this as n to the 3/2, right? Because this is n to the 1, that's n to the 1/2. You add the exponents. So this converges by p-test. This, 3 up here, and then 2, n to the 1/3. Oh, I guess I'm losing my limits here. N equal 1 to infinity. Okay, so this p is less than 1, so this diverges by p-test. This here, this is the same as saying 3 to the 1 over n. This is not p-test, is it? No, done this lots of times, so hopefully you're almost getting it memorized. This is test for divergence. If I take the limit of this, I get 5 over 3 to the 0. That's 5. That doesn't equal 0, so this diverges by T for D. This here, I can see the p is 3, so this converges by p-test. And so now we have n to the pi. Well, pi is a number that's bigger than 1, so this converges by p-test. And this is e to the n. This is not p-test, right? P-test is n to the p. What do I do with this? So I can pull that pi on the outside. Sometimes it's helpful so you don't have numbers in the way. Oh, this is a number to the nth power. This looks like it's geometric. And I can see that the a is going to be 1 over e, the r is going to be 1 over e. So I can see that it's going to converge by geometric. Doesn't say find the sum, so you just need to identify what the r is, and so you can say converges.